So in this video we'll prove the divergence theorem, and for proving the divergence theorem I have drawn a box and I've drawn the coordinate axis. This is our x-axis, this is our z coming out of the plane of paper and in upward direction. This is our y-axis. I have marked the planes. This plane I've marked as 1, this plane I've marked as 2, this is 3, this is 4, and the plane facing us, this is 5, and the plane just opposite to that is plane 6. So let us consider a vector field. Say it is given by C, and say it has components Cxi plus Cyj plus say Czk. I have not written it out explicitly, but Cx, Cy and Cz, they are all functions of position, all of the positions, that is x, y and z. So for instance, Cx is a function of x, y, z. Similarly, Cy and Cz, they are also functions of x, y and z. So the vector field changes from point to point, both in terms of magnitude as well as in terms of direction. So at different points we have different vector lengths pointing in different directions. So what we have to find out here, we need to find out the flux of C through this box. So we have to find out the flux of C through this box. So for doing that, let us first find out what C dot dA, that is the flux of C through the surface 1 is. So if we dot C with the small area vector dA, you'll have to first of all note that this box is infinitesimally small. So in doing C dot dA, we'll have to multiply the component of C which is in the direction of the area vector dA, or exactly in this case it will be exactly opposite to the direction of the vector dA. For this plane, the area vector dA will be pointing in the negative x direction, and we'll have to take the x component of C, which is Cx. So this will become minus of Cx times the area of this. So to find out that area, one of the sides, this side is a small increment in the along the z axis, so this is delta z. There's a small increment along the y axis, that's delta y. So this becomes minus of Cx times delta y delta z. Similarly, if we have to find out what the flux through this surface is, again we'll have to take the x component of C. You'll have to remember that Cx is a function of x, y and z. So C dot dA over surface 2 will be plus of Cx times delta y delta z, because in this case the small area vector will point out of the box and normal to the surface 2. So if we add up these two terms, we'll get, okay, one thing I've missed here is that in doing this integral, I'll have to take that component of Cx, that component of C which is along the x-axis, that is Cx, and we will have to assume that Cx is constant over this entire surface, because this surface is very small. So we can say it is Cx at surface 1. Actually we can approximate the values of Cx over this entire surface by the value of Cx which is at the center of the surface. In any case, we call it Cx1, that is the approximate constant value of Cx over the surface 1. Similarly, this will be Cx over the surface 2. we have approximated the value of Cx over this entire surface by the value of Cx at the center of the surface, and we call that Cx2. So if we add up these two terms, we get Cx2 minus Cx1 all times delta y delta z, but we can say that Cx, so this is Cx2 and here we have Cx1, so Cx2 to the first approximation it is equals to Cx1, but to the second approximation it is rate of change of Cx with respect to x times delta x, this length being delta x. So this is our delta x right here, this much is delta x. Therefore Cx2 minus Cx1 is just this. So adding up the fluxes over these two surfaces, we have delta Cx over delta x times delta x, delta y, delta z, which is actually delta v or dv if we let delta x, delta y, delta z go to 0. Similarly, if we let us say find out the sum of the fluxes from say these two surfaces, this one and the upper one, we can say that integration of c dot dA over surface 3. So in this case, the component of c, which is parallel to the area vector, is the y component. So we have a cy at surface 3 multiplied by these two sides, which is the area of the surface 3, delta x, delta z. Similarly, c dot dA over surface 4 is just cy. Okay, we have a minus sign in the previous equation because cy by definition will point towards positive y-axis while the area vector is out of the box along the negative y direction. So cy at surface 4 times delta x, delta z, and this time we have a positive sign because cy and the area vector, small area vector, point in the same direction. If we add these two up, we have cy at surface 4 minus cy at surface 3 times delta x, delta z, but we can say that cy at surface 4 to the first approximation it is equals to cy at surface 3, but to the second approximation it is the rate of change of cy with respect to y times delta y. So cy4 minus cy3 is just this term, so that becomes partial of cy with respect to y times delta v. And similarly for the fifth and the sixth surfaces, I'll get partial of cz with respect to z times delta v. So the surface integral will amount to the sum of these three terms. So if I add them all up, what I get is the sum of these three terms. So that is delta cx or partial of cx with respect to x plus partial of cy with respect to y plus partial of cz with respect to z times dv if I let all the lengths go to 0. And you will also have to note that let us say first of all this derivative or this derivative here, where is this derivative being calculated? It is being calculated over here, where cx has been assumed to be constant at cx 1. Again, this derivative is being calculated here, where cy has been assumed to be constant at cy3, but ultimately we'll let all these lengths go to 0. So the dimensions of this box go to 0, and all the derivatives are ultimately calculated at this point, x, y, z. So this is our surface integral for the infinitesimally small surface. And this can be written as grad dot c dv. This is just for the small surface. If we have a large surface which we can divide into an infinite number of cubes, and we use this for each cube and then add all of them up on both sides of the equation, we'll ultimately get, for the bigger surface, integration over the bigger surface S, the surface which has finite dimensions, c dot dA. This is being done over the volume. So this becomes a volume integral. Integration over the volume which is enclosed by this surface, grad dot c dv. So this proves divergence theorem.